So for this problem, we're working with Taylor series, specifically for the function f of x equals 1 over x, which is centered at x equals 2. To get started, I want to actually pull up our formula for our Taylor series right from OpenStax. If f has derivatives of all orders at x equals a, then the Taylor series for the function f at a is defined to be the infinite series, which is a collection of the derivatives of f at a divided by n factorial times the quantity x minus a raised to the nth power. A Taylor series is an infinite polynomial expression that approximates the function itself. So let's go ahead and let's calculate this Taylor series. We're using the function f of x equals 1 over x. The very first piece that I want to note is that the Taylor series has these little components, one of which is our first derivative. So we have to focus in on our, not our first derivative, but our n derivatives. So we've got our derivatives. That's being one piece of this series. The second piece is the factorial piece. And then the third piece, that's the part that creates our infinite polynomial, the x minus a to the nth power. I want to put all three of those pieces into my problem, but I'm going to start and focus first of all on our derivatives. Let's start by writing down then f of x equals 1 over x. And we know we're going to be taking derivatives, so I want to rewrite 1 over x as x to the negative 1 power so I can apply my power rule. All right, so if I start with f of x equals x to the negative 1, then my first derivative is actually, what is that? That's negative x to the negative 2 power using our power rule, which I could also look at if I want to as negative 1 over x squared. My second derivative, what is that equal to? Well, that's equal to negative 2 times negative 1, or 2x to the negative 3, or 2 over x cubed, again using our power rule, right? Our third derivative, negative 3 times 2 is giving us negative 6, subtract 1 gives us negative 4. Or negative 6 over x to the 4th. Our fourth derivative, that's going to be positive 24 x to the negative 5th, which is 24 over x to the 5th, etc., etc., etc. So what we're creating right now are our derivatives. We want to evaluate those derivatives at the specific point 2. So when x is 2, hang on. Getting a little ahead of myself here. So when x is 2, then f of 2 is just 1/2, or 2 to the negative 1. F prime of 2 is negative 1 over 2 squared, or negative 1/4. The second derivative of f at 2 is just 2 over 2 cubed, which is just positive 1/4. Our third derivative at 2 is negative 6 over 2 to the 4th, or negative 6 over 16, which reduces down to negative 3 over 8. Our fourth derivative at 2 is just 24 over 2 to the 5th, which is 24 over 32. And if we divide top and bottom by 8, if we divide top and bottom by 8, that gives us 3/4. What we have done is let's go back quickly. For our Taylor series, remember we've got different pieces, and right now I'm just focusing on our derivatives at a. The other piece we have to worry about is our n factorial. I can look at that as 1 over n factorial, and so now let me combine the derivatives with 1 over n factorial. So taking now our derivatives and combining it with 1 over n factorial, we get the following. We start with our first derivative, which is 1/2, and we're going to multiply by 1 over n factorial. Now, this is where it's going to get a little complicated. So now we want to put in our piece 1 over n factorial. We're looking for our first 5 non-zero terms, remember. Okay, so I want to add a little bit here to the side. Over here, we weren't taking a derivative, and n was 0. Here we are taking our derivative, that's n equals 1. Here we're taking our second derivative. Here we're taking our third derivative, and here we're taking our fourth derivative. So when I go to compute 1 over n factorial, I have to be aware of what value I am for n in which position. At the very first term, remember, we didn't take a derivative, and therefore n was 0. So that means I'm going to take f of 2, which is 1/2, times 1 over 0 factorial. For the second term, I'm going to have negative 1/4 times 1 over 1 factorial. For the third term, I'm going to have positive 1/4 times 1 over 2 factorial. For the next one, I'm going to have negative 3 over 8 times 1 over 3 factorial. And then for the last one, it's going to be 3/4 times 1 over 4 factorial. So what happens when we simplify? Well, let me scoot over a little bit, and let's see what happens when we simplify. We're continuing now to work on this factorial piece, right? Well, 0 factorial is just 1. So that's 1/2 times 1, which is just 1/2. 1 factorial is also 1. So both 0 factorial and 1 factorial are defined to be 1. Therefore, my second term is going to be negative 1/4 times 1, or just negative 1/4. 2 factorial can be thought of 2 times 1, right? 2 factorial. Factorials are, let's just make sure we know what factorials are. I'm pretty sure we're familiar with factorials, but let's just remind ourselves. A factorial means start with the number and then multiply by 1 less, and then multiply by 1 less, and then multiply by 1 less. So if I have 2 factorial, that's going to be 2 times 1 less, or just 2. So that's 1/4 times 1/2, or 1/8. Now we get a little more complicated here, right? We've got negative 3/8 times 1 over 3 factorial. Well, let me expand 3 factorial. 3 factorial is 3 times 2 times 1. And if you allow me, I'm going to, undo that. That was a mistake. I'm going to go ahead and I want to cancel out this 3. So that shows me that if I take negative 3/8 times 1 over 3 factorial, it's going to give me negative 1 over 2 times 1 times 8, or 16. And let's expand out that bottom. 4 factorial. 4 factorial is 4 times 3 times 2 times 1. Again, I'm going to cancel out that 3 from the 3/4. And that's going to tell me that 3/4 times 1 over 4 factorial is just 1 over 4 times 4, which is 16 times 2, which is 32. Wow, do you see a pattern developing? Do you see a little bit of a pattern developing? Well, all right, well, we'll see. Okay, so those are our coefficients. That's the second piece, the factorial piece. But let's go back to our actual Taylor series again. So we've looked first of all at our derivatives. That was the first piece. Now we've computed our factorials. That was the second piece. And the last piece to creating a Taylor series is the actual polynomial piece, which is x minus a to the n. Remember, we're centering at 2, so we're going to have x minus 2 to the nth power for each term, depending on what n is. So let's go back to our work. And let's continue. So now to get our first 5 non-zero terms, we must take and multiply by this x minus 2 to the nth. Let me write that down. We're multiplying by x minus 2 to the n, depending what n is. So for this first term, it's going to be x minus 2 to the 0th power. But x minus 2 to the 0th power, anything raised to the 0th power is 1. So really, our first term just happens to be 1/2. The second one is going to be x minus 2 to the first power. The third one is going to be x minus 2 to the second power, x minus 2 to the third power, and then x minus 2 to the fourth power, because on the very bottom, n was 4. Those are the pieces which we put all together to give us the first 5 non-zero terms in our Taylor series. 1/2, negative 1/4 times x minus 2 to the first, 1/8 times x minus 2 to the second, negative 1/16 times x minus 2 to the third, and 1/32 times x minus 2 to the fourth. Let me put those pieces, and that's what's going to go right here in these boxes on my open math. 1/2, and then negative 1/4 x minus 2, and then positive 1/8 x minus 2 squared, then negative 1/16 x minus 2 to the third, and positive 1/32 x minus 2 to the fourth. Those are our first 1, 2, 3, 4, 5 non-zero terms for our Taylor series. Now the second piece is to write this series compactly. So I just want to give us some space here to show this is what we have to work on next. But do you see a pattern that has developed? What do you notice is happening in each term? Well, first of all, I have an x minus 2 to a power, right? So I'm going to write down x minus 2 to some power. All right, but we have one little tiny confusing piece. We have n minus 1 down here. We started with n equals 0. So because we're starting up top in my open math with n equals 1, our n now is a new n, different than the other n from our Taylor series formula. So scratching our old remembrance of what these values are, we're going to focus right here. For this part here where we're rewriting the series, our first term is n equals 1. Our second term is n equals 2. Our third term is n equals 3, n equals 4, and n equals 5. So for writing our compact series, because my open math is giving us n equals 1 to start, we're going to have to reformulate our actual thought process when we go to write compactly what this Taylor series is. But that's not too bad. If I'm looking right here and focusing in on my exponents, If I'm looking here and focusing in on my exponents, what do I note? Well, 4 is actually 1 less than 5. 3 is 1 less than 4. 2 is 1 less than 3. And so really what I could do as an exponent up here on my x minus 2 piece, I can put n minus 1. And this will correctly describe what's happening for each of our terms. What about the stuff in front? What about our coefficients? Do you see a way to describe the numbers 1/2, negative 1/4, 1/8, negative 1/16, and 1/32? Well, notice 2, 4, 8, 16, 32. Those are all powers of 2, aren't they? Specifically, 32 is 2 to the 5th. 16 is 2 to the 4th. 8 is 2 to the 3rd. 4 is 2 to the 2nd. 2 is 2 to the 1st. You see a pattern? When n is 5, I have 2 to the 5th in the denominator. When n is 4, I have 2 to the 4th in the denominator. So it seems fitting that I have 2 to the nth depending on where I am along those terms in my Taylor series. Okay, one more piece we have to deal with, that being this negative. It's an alternating series. Notice we go from positive to negative, positive to negative, positive to negative, etc. And we know that to create an alternating series, we have to use negative 1 to the n or negative 1 to the n plus 1 or n minus 1. What I do know is that when n is 5, let me focus in. When n is 5, we'll keep working on the back end again. When n is 5, I have a positive 1. When n is 4, I need a negative. But remember, in order to get the negatives, we actually have to have negative 1 being raised to an odd power. So negative 1 being raised directly to the 4th power is not going to work. We're going to need an n minus 1 here in front. And so it looks to me like we could write our compact series using this formula right here. Negative 1 to the n minus 1 over 2 to the n times the quantity x minus 2 to the n minus 1. You could also have written it as negative 1 to the n plus 1 times x minus 2 to the n minus 1 over 2 to the n. That would also be acceptable. Oh my goodness gracious, that was a lot of work, but I hope it makes sense. If you have any questions at all, please don't hesitate to email and reach out. Have fun working with Taylor series. As I mentioned before, they're very, very important. Good luck.